To calculate the electrical load for the water company project involving fluorescent lights, receptacles, and a sump pump, we will proceed step by step. Firstly, we'll determine the individual circuit loads. For the fluorescent lights, identified as circuit 1, the calculation starts with 0.78 amps multiplied by 4, giving us a ballast draw. Then we multiply this result by 120 volts, yielding 375 volt amps. Since this is a continuous load, we increase it by 120%, resulting in 450 volt amps. Secondly, circuits 2 and 4 each consist of 2 receptacles. Each receptacle is rated at 180 volt amps, so 2 receptacles contribute 360 volt amps per circuit. Thirdly, for the sump pump, which is circuit 3, it's rated at 3/4 horsepower and draws 13.8 amps. Multiplying 13.8 amps by 120 volts gives us 1656 volt amps. After figuring each of the loads, we proceed to calculating the total non-continuous load. Non-continuous loads are those that do not operate continuously, here being the receptacles. The non-continuous load is determined by adding the loads of circuits 2 and 4, both consisting of receptacles. Because there are a total of 4 receptacle slots, the total non-continuous load is 360 volt amps multiplied by 4, equaling 1440 volt amps. Now to calculate the total load, we add the continuous and non-continuous loads. The continuous load consists of the lights and the sump pump, which is 450 volt amps and 1656 volt amps respectively, totaling 2106 volt amps. Adding the non-continuous load of 1440 volt amps gives a total load of 3546 volt amps. Next, we need to convert this total load into amps. We divide the total load in volt amps by the voltage. Thus 3546 volt amps divided by 120 volts equals 29.55 amps. Finally, we calculate the neutral load. The neutral load is the sum of the currents in the individual circuits that share the neutral conductor. In this scenario, it includes the lights in circuit 1 and the sump pump in circuit 3. The neutral load is calculated by adding 4 times the current draw of the fluorescent lights to the current draw of the sump pump. Thus, 4 multiplied by 0.78 amps plus 13.8 amps equals 18.98 amps. Therefore, the total load is 29.55 amps, and the neutral load is 18.98 amps. It's important to note that we do not divide the total load or neutral load by 220 volts in this calculation. This is because the system is single phase, and the 120 volt load serves as the reference point for these calculations. This comprehensive approach ensures accurate load calculations for the water company project, ensuring both safety and code compliance. This breakdown covers the calculation of individual circuit loads, total non-continuous load, total load, current conversion, and neutral load determination, providing a clear understanding of the electrical requirements for the project. Always refer to local electrical codes and regulations for specific requirements and guidelines. Ensure all electrical work is performed by qualified and licensed electricians. The load calculation process is crucial for safety and compliance. It involves determining the total electrical demand of a building or system to ensure that the electrical service is adequate. Firstly, calculate the general lighting load. This is usually based on the square footage of the building. Refer to the National Electrical Code, or NEC, to find the volt amp per square foot requirement for the specific type of occupancy. Multiply the square footage by the volt amp per square foot value to get the total volt amps for lighting. Secondly, account for receptacle outlets. For general use receptacles, the NEC typically requires a minimum of 180 volt amps per outlet. Count the number of receptacle outlets and multiply by 180 volt amps to determine the total volt amps for receptacles. Thirdly, consider fixed appliances. This includes appliances such as water heaters, air conditioners, and electric ranges. Obtain the nameplate rating for each appliance, which will indicate its volt amp or wattage. If the rating is in watts, divide by the voltage to get the current in amps, then multiply by the voltage to get the volt amps. For motors, use the motor's horsepower rating and the appropriate NEC table to find the full load current. Multiply the full load current by the voltage to get the volt amps. Fourthly, factor in heating and cooling loads. For heating and cooling systems, determine the total volt amps for each unit. This information can be found on the unit's nameplate. If the heating system is electric resistance heat, the load is considered continuous and should be multiplied by 1.25 to account for the continuous load requirement. Fifthly, calculate the demand factors. The NEC allows for demand factors to be applied to certain loads. Demand factors are multipliers that reduce the calculated load based on the likelihood that all loads will not be operating at the same time. For example, the NEC allows for a demand factor to be applied to the general lighting load in dwelling units. Sixthly, determine the feeder and service size. Once all the loads have been calculated and the appropriate demand factors have been applied, add up all the individual loads to get the total calculated load. Divide the total calculated load in voltamps by the voltage to determine the total current in amps. Use this current to select the appropriate size feeder and service conductors and overcurrent protection devices, such as circuit breakers or fuses. Refer to NEC Table 310.15. E16 to determine the ampacity of conductors based on their size and insulation type. 7. Consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause appliances to operate inefficiently or not at all. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. Eighthly, check for code compliance. Ensure that the load calculation complies with all applicable requirements of the NEC and local electrical codes. This includes requirements for conductor sizing, overcurrent protection, grounding, and bonding. Ninthly, document the load calculation. Keep a record of the load calculation, including all assumptions, calculations, and references to the NEC and local codes. This documentation will be helpful for future reference and for demonstrating compliance with electrical codes. 10th, review and revise. Periodically review the load calculation and revise it as necessary to reflect changes in the electrical system, such as the addition of new loads or the removal of existing loads. This will help ensure that the electrical system remains adequate and safe. Remember that electrical load calculations can be complex and require a thorough understanding of electrical principles and the NEC. If you are not familiar with electrical load calculations, it is best to consult with a qualified electrician or electrical engineer. They can help you accurately determine the electrical load and ensure that the electrical system is safe and compliant with all applicable codes. In the specific scenario presented, we have a 100 amp service for a water company at a vault that monitors flow. The electrical loads include fluorescent lights, receptacles, and a sump pump. We must calculate the total load and neutral load to ensure that the 100 amp service is adequate. The steps outlined above provide a systematic approach to performing this load calculation. Starting with the continuous load of the fluorescent lights at 450 volt amps, we determine the demand for lighting. Next, we calculate the receptacles at 360 volt amps each, totaling 1440 volt amps. The sump pump contributes 1656 volt amps. Adding these loads together gives us the total load. Demand factors are not explicitly mentioned, but it is important to consider whether any demand factors apply based on the specific circumstances and the NEC. Finally, we must calculate the neutral load, which is the sum of the currents in the individual circuits that share the neutral. This information is used to select the appropriate size neutral conductor. By following these steps and referring to the NEC, we can accurately calculate the electrical load and ensure that the 100 amp service is adequate for the water company's needs. Remember to document all calculations and assumptions and to consult with a qualified electrician or electrical engineer if you have any questions or concerns. The process of electrical load calculation involves several key steps to accurately determine the electrical demand of a system. Firstly, you need to identify all the loads that will be connected to the electrical system. This includes lighting, receptacles, appliances, motors, heating and cooling equipment, and any other electrical devices. For each load, you need to determine its volt-ampere, or volt-amps, rating. The volt-amp rating is a measure of the apparent power consumed by the load. It is typically found in the nameplate of the equipment. If the nameplate only provides the wattage, you can calculate the volt-amps by dividing the wattage by the voltage. Secondly, after identifying all the loads and determining their volt-amp ratings, you need to classify each load as either continuous or non-continuous. A continuous load is defined as a load that is expected to operate for 3 hours or more at a time. Examples of continuous loads include lighting in commercial buildings, heating and cooling equipment, and some industrial processes. Non-continuous loads are loads that are not expected to operate for 3 hours or more at a time. Examples of non-continuous loads include receptacles, small appliances, and some motors. Thirdly, for continuous loads, you need to multiply the volt-amp rating by 1.25 to account for the fact that continuous loads are expected to operate for extended periods. This is required by the National Electrical Code, or NEC, to ensure that the electrical system is adequately sized to handle the continuous load. Fourthly, after adjusting the volt-amp ratings of the continuous loads, you need to apply demand factors to the loads. Demand factors are multipliers that reduce the calculated load based on the likelihood that all loads will not be operating at the same time. The NEC provides demand factors for various types of loads depending on the occupancy and the number of loads. For example, the NEC allows for a demand factor of 0.70 to be applied to the first 10 kVA of electric space heating load in a dwelling unit. This means that only 70% of the electric space heating load is considered when calculating the total load. Fifthly, after applying demand factors, you need to add up all the individual loads to determine the total calculated load. This is the total volt-ampere demand that the electrical system must be able to handle. Sixthly, based on the total calculated load, you can determine the required size of the service entrance conductors, the overcurrent protection devices, and the other components of the electrical system. The NEC provides tables and guidelines for selecting the appropriate size conductors and overcurrent protection devices based on the ampacity of the load. Seventh, in addition to calculating the total load, you also need to calculate the neutral load. The neutral load is the portion of the total load that is carried by the neutral conductor. The neutral load is typically less than the total load because some loads, such as three-phase motors, do not contribute to the neutral load. The NEC provides guidelines for calculating the neutral load, depending on the type of loads and the type of electrical system. Eighth, it is important to note that electrical load calculations can be complex and require a thorough understanding of electrical principles and the NEC. If you are not familiar with electrical load calculations, it is best to consult with a qualified electrician or electrical engineer. They can help you accurately determine the electrical load and ensure that the electrical system is safe and compliant with all applicable codes. Ninthly, documentation is crucial. Keep a record of all calculations, assumptions, and references to the NEC. This will be helpful for future reference and for demonstrating compliance with electrical codes. 10th, periodically review and revise the load calculation to reflect changes in the electrical system, such as the addition of new loads or the removal of existing loads. This helps ensure that the electrical system remains adequate and safe. In the specific scenario presented, we have a 100 amp service for a water company at a vault that monitors flow. The electrical loads include fluorescent lights, receptacles, and a sump pump. We must calculate the total load and neutral load to ensure that the 100 amp service is adequate. By following the steps outlined above and referring to the NEC, we can accurately calculate the electrical load and ensure that the electrical system is safe and compliant with all applicable codes. Remember to consult with a qualified electrician or electrical engineer if you have any questions or concerns. Consider the impact of harmonics on electrical systems. Harmonics are distortions of the sinusoidal voltage and current waveforms that can cause problems such as overheating of equipment, increased energy losses, and malfunction of sensitive electronic devices. Harmonics are typically generated by nonlinear loads such as electronic ballasts, variable frequency drives, and computers. To mitigate the effects of harmonics, you may need to install harmonic filters or use harmonic reducing equipment. Always verify the local voltage levels and the service type. The voltage level and service type will affect the load calculation. For example, if the service is 208 volts instead of 120 volts, the current will be lower for the same amount of power. The service type, such as single-phase or three-phase, will also affect the load calculation. When performing electrical load calculations, it's crucial to adhere to established practices to ensure accuracy and safety. Firstly, start by creating a detailed inventory of all electrical loads that will be connected to the system. This includes lighting fixtures, receptacles, appliances, motors, and any other electrical equipment. For each load, gather information such as its volt-amp rating, voltage, and whether it's a continuous or non-continuous load. Secondly, use appropriate load calculation methods based on the type of electrical system and the applicable codes and standards. The National Electrical Code, or NEC, provides guidelines for calculating electrical loads in various types of buildings and occupancies. Follow these guidelines carefully to ensure compliance. Thirdly, apply demand factors judiciously. Demand factors are multipliers that reduce the calculated load based on the assumption that not all loads will be operating at the same time. However, be conservative when applying demand factors, especially in critical applications where reliability is paramount. Fourthly, consider future expansion. Design the electrical system with enough capacity to accommodate future growth and expansion. This will prevent the need for costly upgrades later on. Fifthly, verify the accuracy of your calculations. Double-check all calculations to ensure that they are accurate and consistent. Use software tools or spreadsheets to automate the calculations and reduce the risk of errors. Sixthly, consult with qualified professionals. If you're not experienced in electrical load calculations, seek assistance from a qualified electrician or electrical engineer. They can provide valuable insights and guidance and help ensure that the electrical system is designed safely and effectively. Seventh, document all assumptions and calculations. Keep a detailed record of all assumptions, calculations, and decisions made during the load calculation process. This documentation will be useful for future reference and for demonstrating compliance with codes and standards. 8. Review and update the load calculation regularly. As the electrical system changes over time, review and update the load calculation to reflect those changes. This will help ensure that the system remains adequate and safe. Ninthly, consider the impact of special loads. Special loads, such as electric vehicle charging stations or large industrial equipment, may have unique load characteristics that require special consideration. Consult with experts and follow manufacturers' recommendations when dealing with these types of loads. Tenthly, address any potential safety concerns. Pay close attention to safety considerations during the load calculation process. Ensure that the electrical system is designed to protect against overloads, short circuits, and other electrical hazards. Electrical load calculations are a critical aspect of electrical system design. By following these practices and seeking assistance from qualified professionals, you can ensure that the electrical system is safe, reliable, and compliant with applicable codes and standards.